Okay, so last time we were talking about Apple CPUs. Well, we were talking about mobile CPUs in general, and specifically leading up to that, the idea of multitasking, and how in the early mobile specific operating systems, again, keeping in mind that the job of an operating system is to sit as an intermediary between the user and the hardware. um, Android chose a bunch of desktop approaches for their operating system in a rush to get it to market, which ended up being detrimental to battery life and user experience and stuff like that. Apple had created an operating system that was mobile first, that from a consumer perspective maybe was missing some features that they assumed should be there for all computers, but we might say they were missing for some reasonable reasons. Not everybody saw it that way when it was first happening. There was complaints, and this was probably actually the part of the reason for the popularity of Android early on, even though it was a significantly worse product early on. But eventually, both had multitasking, and both kind of got rid of the things that were extra bad and added the things that were kind of expected by users. And this was all driven by battery technology and that kind of stuff. So as our batteries got better and better and better, we were able to get more things going on at once. Obviously, that's also related to the processor. Faster your processor, the more you can fake out the end user that more than one thing is happening at one time. We have to think about the nature of the processors that are in these smartphones. So, it's one thing to think about the history of CPUs for desktop computers. A very similar argument is happening when we're talking about desktop. When you're talking about desktop computers, you're designing chips that don't take into consideration running off of a battery. And for a long time, they were still single core processors, but then they quickly became multi-core. Before you had multi-core, you had multi-processor. So you had two physical processors and that kind of thing. So mobile was a little bit slower to catch up to that. And I brought up a thing here that talks about the so in the first several generations of iPhone, the first couple, I think, they were using the same chips as the Android was the first year, which was something from Qualcomm, more than likely. So then Apple started releasing their own processors, and we're seeing the list of their processors here. We're going to spend quite a bit of time talking about their M1 processors, their newer stuff, which becomes very interesting, and that's more focused on laptops at this point. But the M1 is also in iPads. But when we just click on one of these guys, so this Apple A4 processor was originally introduced for the iPhone 4. iPhone 4 was Apple's third iPhone. You had the original iPhone, you had the iPhone 3G, actually it was the fourth. You had the iPhone 3G, iPhone 3GS, and then iPhone 4. This is the first time they had their own, what they always reference as, we have our own silicon in our iPhones. So they're making the processors, or some company they acquired is making the processors. They mentioned it was in the original iPad. So this the mentality for this A4 is when Apple first released the iPad. Oh, interesting. It was announced on my birthday. When they announced the original iPad, that's when they introduced the idea of this new processor that does some things, whatever that means. All right, so when we look at the specs of this processor over here, we see that, Apple developed it, Samsung fabricated it in one of their factories. This is where we start caring about things. So a couple of things here that are interesting to us. First of all, the single core versus multi-core. So if we hop over here, we just say CPU cores. So this is a single physical processor with one or more processing units. A processing unit can perform I'm going to just say single like that because it gets a little bit blurry when you add in things like pipelining and some other interesting tricks to squeeze as much performance out of a processor as you can. But a processing unit can perform a single task at a time. So what does this mean? It means that multiple cores can perform multiple tasks at the same time, provided that those tasks logically can happen at the same time. Okay, so a couple of interesting things there. All right, so what are some of the side effects? Like, we might say, okay, well, more cores is always better than one core, something along those lines. Well, I mean, we could say we start comparing this to real life. And we say, okay, if you're changing, the proverbial changing a light bulb problem, if you have 20 people all willing to help change a light bulb, does that really change a light bulb any faster than a single person who's there to change the light bulb? In some examples, it might actually be slower if depending on the speed of those folks who are changing the light bulb. Now you might say, well, why would the speed be different? And we'll kind of talk about that here in a second. But some tasks do not lend themselves to multiple people doing them at once and actually having an improvement. Shoveling snow, Wisconsin's winter pastime, that's something where having multiple people work on it is going to be a time saver. You'll get things done more quickly. Now, the cost, though, of multiple cores. So multiple cores will cost more power, give off more heat, and require other, well, let's say require increased resources from other parts of the computer. Okay, so all of these things add up to just saying, oh, let's throw more cores in here really isn't such a no-brainer. Even if you are capable of creating more cores, you have to consider, is the juice worth the squeeze? Me having more cores in this processor, is that going to get me a performance boost that I did not have before? Or is it actually going to degrade my user experience? Especially when we look at the cost more power. In the earlier days of mobile, and even today, but our batteries in mobile have gotten pretty good. It seems like every new device that comes out is, sporting the latest, greatest Ferrari graphics card and stuff like that. So, we've kind of made the decision of how long does a phone really need to last? We don't need our phone battery to last a week. Most of us are charging it daily, let's say. So we now are in the process of saying, let's get more power out of these devices, even though we are slowing, even well, let's get more power out of them, even though we aren't extending our battery life, as long as we maintain the battery life we had before. But certainly in the earlier days, and even up until more recently, if we have multiple cores, which is costing more power, that has some effects to us. Because one of the other things that we saw, let's say primarily from Apple, but we see it from a lot of different companies, is we can say device size. And if we kind of just keep the focus here on Apple, because I think they tend to be a good example for this, is, Apple tries to make their devices as sleek, thin, etc. as possible. So that means if you're going to put higher power processors in there, and you're going to say, okay, well, now we need more power. And now you're going to say, Apple, you need to put a bigger battery in there, because even though we had the battery technology, that might be reasonable. You can always extend battery life by putting a bigger battery. I think I referenced last time that, funny memes that were out kind of in the early days of Android were like people carrying around a car battery in a backpack to keep their Android device going. All right, so nothing prevented you from having a battery equivalent of the size you'd put in a laptop computer on your smartphone, which would then extend its battery life because you have a bigger battery, except the fact that you want the thing to fit in your pocket. So you had some physical limitations that went into how big of a battery could you possibly put in there. And that's why it was so important to sometimes wait for battery life, especially when you had certain designers at the time in the original kind of the first phase of smartphones. Everything was about shrinking these things down so they fit in your pocket better and better and better. You got the same all-day battery life or close to all-day battery life as you did with the bigger device in a smaller device. All right, so that was the move we were making. More recently, we're making a little bit different moves, or creating 2 or 3 different size devices depending on user preference, not necessarily driven by the companies themselves. All right, so one is power. Next one is heat. You start putting more cores in there, now you're giving off more heat. Well, what's the consequence of more heat? Well, we can just generically say that when it comes to computer architecture, heat is bad. that's an overarching thing. Heat is bad. So we have to have some way of moving heat away from processing units, because the hotter it gets, the more, let's call it, error prone it gets. And then you also are going to have hardware failures and things like that, where it completely stops working. So heat is bad. So then what does that mean? Well, we need to have some way of dissipating the heat. Well, if you're inside of a laptop, and all of you have probably heard this before at some point in your laptop, sometimes if you're doing something extra stressful, all of a sudden you hear all the fans kick on, right? And they're working 1,000 miles an hour, and the fans are trying to cool. And even if you didn't feel like the laptop was getting overheated, the reason you didn't think it was getting overheated is because the fans were working so hard and they were moving that heat out and away from the inner components. Probably your number one source of heat inside of any device is going to be the processor. If you look inside of let me just pop this open here. Let's see, Core i7 desktop CPU. Let's see if we can get a picture with a heatsink. There we go. This will work. See if we get any sort of show these in a couple of, well, yeah, this one kind of shows it. Let's show this picture first. All right, so this is a computer motherboard. So when you look at, if you've built computers before, you've seen this kind of thing before, but, this is for a desktop computer. So this guy's your actual processor. It's a Core i7 processor, pretty a very new one. So this probably has 12 logical cores in it, maybe even 18 logical cores in it. So we're not just talking about one or two at this point, but that part doesn't matter. The physical sizes of the processors have not really changed, and we'll talk about that here in a minute some more. But you have your actual processor that's sitting in there, and then on top of that, you have this heat sink thing. And then over here, this is where your RAM goes, and we'll talk about the nature of the different memories that are inside of our computer here today and into next week. And then we're going to get into ARM-based assembly programming after that. Here's kind of a side view of maybe what we're looking at. Maybe it's a little bit different product, but roughly the same thing. You have this device that sits on top of this part of the motherboard. So your processor sits in this little square thing, probably I don't know, an inch and a half by an inch and a half, something like that, 2 inches by 2 inches ish square. And then you put that in there. Then on top of that, you put this, probably four or five, could be even bigger thing on top of it. And typically that thing has these metal fins that are coming off of it. And those fins are meant to dissipate heat. And you have this fan that helps push the heat across those fans and out away from the processor. All right, so, and then even within that, if we go one step further and we do desktop liquid cooling, get a decent picture of this. Yeah, this kind of shows some, I think this kind of shows a fairly obvious one. So you see all these tubes, you kind of have a reservoir for liquid, and it has a pump. And what it's doing is it's pumping water across all these heated, the heat sources inside of your computer, and then water moving also moves the heat away. This would be better cooling, but at the cost of having to have a water pump inside of your computer. So you could imagine that you can the idea of dealing with heat is a big problem. And the more powerful your equipment is, they're showing these things here. Our previous picture, we had like a giant graphics card. Well, here I'll even let's do a 3090 GPU. So, these are graphics cards, and just to give you an idea of scale, this is a human holding one of those graphics cards. Okay, so when you're thinking about the GPU, the thing that drives the graphics inside of your computer, none of you are going to want a smartphone that is anywhere near the size of just that graphics card, right? So just consider all of those decisions that we have to make when we drop down to a mobile device, whether it's a laptop, which is kind of our middleman here, or a smartphone. When we're making those trade-offs, that comes with giving up power. To drive a graphics card like this, you're going to have two different power sources coming in. You probably need something like a 1 kilowatt power supply in your laptop. You could probably get away with a little less than that, but I probably wouldn't have a gaming desktop computer that didn't have at least a 1 kilowatt power supply in it. So it's pushing a bunch of energy to the motherboard for the processor, the motherboard for the memory, for tons of electricity for this graphics card. This is going to be the main source of electrical draw, especially when you're playing games and stuff like that. So when you start thinking about, if I just bounce back real quick to our original thing we were looking at with the Apple processors, it's telling us here, the type of, how many cores, how many things can it do at once? That's what we're talking about with this core thing. Then it's talking about the actual architecture, and it runs this thing called an ARM architecture. We're going to talk about that versus. We're going to talk about that versus like Intel architecture a little bit later. But then we drop down one level when we get to the GPU. So this guy lists this chipset for the GPU. This thing's driving the graphics for that guy. Now, obviously, you're not going to. Obviously, you're not going to be playing the latest, greatest version of Call of Duty on your smartphone. But for those of you who use your smartphones for gaming, you probably have noticed that things are getting closer and closer to us doing just that on our smartphones. Smartphones have become gaming devices. If you go to any shopping mall or something like that and just randomly try to find a 12-year-old, you're going to see their face buried in a smartphone, or maybe nowadays an iPad or something, and they're going to be playing games on there. I've watched my nephews do it for years now. So, the first thing they say when you pick them up to take them somewhere is like, give me your phone. And they want to do stuff with it. So, these are certainly trade-offs, even back in that day. I mean, let's jump to the latest, greatest, just to give us the extremes. That was like the first Apple processor, so, we're going to go to the A15 Bionic. So this would be their latest, greatest. So this came out in September of 2021, very recent processor. Should be an example of the best we're able to get into a smartphone. Now, I do want you to keep in mind that no longer is this kind of chip powering the iPads. The iPads are, or that's not the plan. The iPads are moving towards their M1 processors, and then faster, and we'll kind of stumble upon those here soon when we just kind of see the difference. But what I want to focus on here is a modern smartphone processor. What is it bringing to the table relative to kind of what we're talking about here in these desktop processors? Okay, so first of all, we got this whole new category of computing power called neural engine cores. All right, so let's jump here real quick, and what the heck is that? And this is starting to exist on desktop as well. What's a neural engine? Anybody want to give me kind of a guess, or maybe if you do know, when we say neural engine, what are we talking about? Or if you want to replace the word engine, what's a neural network? We got nothing. Some of you have taken artificial intelligence classes. I looked at all the backgrounds. It's just killing me. All right, so when we talk about neural networks,
it's a computer system that's modeled after the human brain or nervous system.
Okay, so it's trying to mimic the human brain, or some kind of brain. You right. Probably started off with, they're saying, okay, well, I think we understand like cat brains and stuff like that better than we understand the human brain. Human brains are pretty complex critters, but yeah, it's modeled after a brain thing. Okay, so now so it looks cool. Okay, so but what's the purpose of modeling it after the brain? Like, why did the people who originally started messing with neural networks, why did they say, hey, let's try to make something that mimics the human brain? What were they trying to accomplish?
They wanted it to allow it to solve computer problems, and because humans are kind of the ultimate problem solvers, and so they wanted to have AI that recognized that.
Okay, yeah. So ultimately, we're always looking for what can our computers do better, right? Just like, and this has almost become a circular problem now. just like as human beings, we say, well, what can we do better? You know, why do human beings use computers? Because as good at, you mentioned we're the ultimate problem solvers, and I agree with that. Human beings are amazing problem solvers. But something I teach in the first semester computer programming classes is we're so good at solving problems that we actually struggle with articulating how we solve them. And one of so the weakness for us is that how do we tell a computer how to solve the problem using some programming language if we can't really dictate, we can't break down into the granular steps how we solve that problem. We just know that we did. We just know that we could, that it was easy, whatever. You know, so there's a whole lot of magic, you know, if you will, trapped inside of that human brain and our nervous system and all the other things that make all of our, you know, elbows and joints and everything bend and, you know, at different timings. So human beings are this really complex critter, and we're good at a whole lot of things, but the more detail you get into, the worse we get. So we're not good at explaining the details of our problems. We're also error prone. So especially doing mundane tasks. So if you are doing even a very simple task, but you're having to do it over a 5-hour period, maybe you're kind of doing like a mini assembly line thing where you're you know, putting together 3 or 4 things, you know, in like a pile and then putting it to the side. Maybe you're putting it inside of a Ziploc bag or something. I don't know, whatever you're doing. As easy as that task might be conceptually, and as easy as it's going to be for a human being to do it once or twice, if you're doing it over and over and over again over a long period of time, it becomes too monotonous for us, and human beings start making mistakes. So that's really where computers step in for us and can do things like that without making those mistakes. So they effectively are augmenting something that we can do, but we can't do as fast as a computer, and we certainly can't do it at a success rate that a computer can do. So we're using a computer to enhance our problem solving, not to replace things that we can't necessarily do. I would say that at least by today's measure, anything our computer can do, a human can do given enough time and maybe a calculator or something like that. You know, then they have to have some way of displaying it on a screen, probably through some soldering irons and things like that. Okay, but there are plenty of things that a human being can do that a computer cannot. And this comes down to a lot of decision making. So neural networks are modeled after the human brain. The goal is to introduce some human-like decision making to a computer that cannot necessarily be described using a traditional programming language. Now, the example I always use when I talk about a problem like this is, you know, all of us in here have had basic math. So if I say, you know, what's 3 times 4, you can give me the answer. What's 5 times 3, you can give me the answer, yada, yada, yada. I think maybe back in 2nd grade, if I remember, we had the flashcards, you know, where you had all the ones table, the twos table, the fives table, you know, whatever it is, and you would learn all those things, and you were kind of memorizing it. And then once you started getting to bigger math numbers, you kind of learned how to do math through like an algorithm formula for doing multiplication, let's say. My first experience with a neural network many years ago was we built used the C programming language to build a model of the human brain, of a very simplified model with you had neurons and you had edges going between the neurons, which were to represent the synapses and all these things like that. And then the way you would, it was called a feed forward neural network. So you fed an input to it. It kind of, went through the neural network in some sort of magical way, and then it spit out an answer on the other end. And what you would have to do is you would have to train that neural network. And what was interesting about this first problem was we were trying to teach this neural network to do something that a computer could already do. We were teaching it how to do simple multiplication. And so what we did is we trained, and we call neural networks, we typically call them models initially. So what we did is we trained a neural network to do the multiplication problem. I trained it on the data that was the 1 through 5's multiplication table. And the way I did that is you just feed it one flashcard at a time, let's say, and it spit out an answer. That answer, the answer it spit out wasn't based on any sort of actual math algorithm or anything like that. It was effectively guessing, just spitting out an answer. If it got the answer right, I wouldn't do anything. But if it got the answer wrong, I'd go back and I tweak the power of those synapses, that were connecting the various neurons, so that hopefully the next time it runs into this exact same problem, it gets a little bit closer to the right answer. You don't want to overcorrect it because then it might get other answers more wrong, but you just wanted to kind of massage it in the right direction. And the idea is you keep feeding it the 1 through 5's table thousands and thousands and thousands of times. And each time you make those little tiny tweaks until in the end, you've created this balanced pot, this model that is kind of perfectly balanced, where if I feed it any of the 1 through 5's multiplication problems, it spits out the correct answer, or at the very least for a high percentage of those questions, it spit out the right answer. So, and then maybe that took 5 or 10 minutes to train the neural network to do that. So in the end, it would start spitting out the right answer. So I effectively had this neural network that knew how to do the 1 through 5's table because I trained it on that. Well, now I took that same neural network that was already trained. It already had all the right numbers associated with the synapses between the neurons. So you can think of it just as a computer object that had a bunch of arrays of things, and all the numbers had been manipulated to just the perfect balance that you feed something in one end, it spits out the right answer somehow magically. A lot of times we call that like a black box, because the logic that's happening inside isn't logical. It's magical, and we call that a black box because you can't really explain what's going on in the inside. It just works. So then I fed it the 6 through 10's multiplication table, and it got, I want to say, either all of them right or all but one of them right. Something, a very high percentage of them it got right, when it had never seen that data before. So what does that tell us? It tells us we effectively trained this neural network the pattern of multiplication, which was just kind of fascinating to me. Now, again, we didn't have to use a neural network to do that because the computer can already do multiplication. But now that we've kind of have a proof of concept, that you can train something for at least some kinds of problems to do something, and it's a new way of solving the problem, but still gives you the correct answer. Now we can start saying, well, what kind of other problems can we give to a computer for solving this kind of stuff? Now, well, for solving other interesting questions. But like I mentioned, even for a simple little thing like that, we maybe would have spent 5, 10, 20 minutes for a little problem like that, training the network with the original data. Now, once you trained it, now you have all the numbers. You don't need to train it again unless you're going to add data to it that unless you feed new data and it's not getting the level of accuracy that you want. Then you got to go back and train it up a little bit more, or make the neural network a little bit more complex. You could add more hidden layers. You could add more neurons, more synapses. You can try to increase its quality of problem solving by tweaking some of the variables associated with the neural network. But once you've trained it, it's kind of good to go. Now, and a lot of times already trained neural networks are called qualifiers. They will already make those decisions, and they'll qualify something into one of the things, or it's a decision tree type of thing. So that was all done in software and took some time, and even feeding things through the neural network you still had to interpret the results. You know, a lot of times the idea was if the correct answer was a 13, I might get a 12.63. So I might decide that my threshold, maybe I just round up anything 0.5 and better, it gets rounded up. So I automatically rounded it up. So I'm still not getting precise outputs. I was getting, when interpreted, accurate outputs. So there's a lot of stuff going there, and we're handling that stuff at the software level. So when we start thinking about bringing a neural engine into our computer, a neural engine is really a hardware representation of what we used to do in software, with the idea that software is slower than hardware. We can just call that a mostly truth. Maybe we can find some sort of example where, depending on the age of the hardware and what it's doing, you might have something in software that's technically faster, but a general rule would be that if something lives in hardware, it's going to be faster than software. But the trade-off is when it's done in hardware, it's hard-coded. It's not changeable. Software is easily changeable. Then we have this kind of thing that lives in the middle called firmware. That's sort of kind of changeable hardware, something like that. But the idea is the closer we get to hardware, the faster something's going to be. So if we're going to start relying on neural networks to do more and more stuff for us in our problem-solving daily lives, having that stuff moved into hardware as much as we can is only going to make that experience that much better. We can think about this from a performance perspective. Why is performance so important? Because some of the things that we're now using neural networks to do, things that we feel that human beings are good at, but computers are not. A good example of this might be like autonomous vehicles. So doing self-driving, so driving a car is something that human beings through practice can get very good at. We have our eyesight, we're taking in a whole lot of things that are going in, and our brain through practice we're making some decisions about how to safely traverse through the world. To now ask a computer to do the same stuff, even leveraging this knowledge that our computers are not, they're not going to miss as much data. Our computer's taking in all that information from all the cameras that it has, and it's going to be working with more data than typically a human being will be working with, because we're only seeing what we're focusing on, what we're paying attention to. Okay, so the computer has all this data, but it still needs to figure out what all this data means and then make decisions based on it. And more so than that, it needs to make the decisions quick enough. We can't decide how to avoid a car accident 15 minutes after the car accident already happened. This stuff needs to be fast. So if we're already moving in a direction where we're going to be solving more and more problems using neural networks, having components of that problem-solving sequence existing in hardware is going to make things faster. So that's kind of the premise for why it has these new features. And these have been around for a couple of years now, these neural engine things, but that's what's going on there. When you get to the CPU, we see that, we actually have 6 cores total. We have 4 high efficiency cores and we have 2 high performance cores. So you read this as, these 2 guys, these do the hard tasks that need a lot of power at the cost of using more battery life. These guys are for the more, less demanding tasks that we're going to do at a lower cost of electricity, energy, things, that kind of stuff. So this processor, even though there's a single physical processor in there, it has 6 different cores, and not all those cores are created equal. Some of them are made for power efficiency, some of them are made for performance. Now you get to the GPU. So again, we looked at a picture a few minutes ago with the NVIDIA 3090 GPU, which is this giant graphics card, and that giant graphics card, would come nowhere near fitting inside your smartphone. It's probably the size of at least 2 or 3 smartphones, probably maybe even more than that. It's big. So that's not going to work. So we need to have some way of giving us what we would call good graphics performance, but inside of a processor. So these graphics cards that are in there, the GPU, graphics processing unit, in this A15, the A15 has graphics built into it, and it has 4 or 5 graphical processing cores dedicated to graphics. So while it's not going to give you a 3090 performance, it's probably going to give you a middle of the road desktop graphics kind of performance on that little phone. And when you look at some of the newer, latest, greatest processors from Apple for their desktop, the M1 processors, which we'll look at, this number of GPU cores goes way up. And they're talking about how their chip can do things at a similar performance to like an NVIDIA 3070. Now we're getting, we're in that same league as that giant graphics card we looked at a few minutes ago. Maybe not quite at that level, but spitting distance. And that's all living just on the chip, and that's pretty impressive. And then the amount of RAM on this thing is the 4 or 6 gigabytes, which might seem small compared to how much is in our computers today, but because things we're doing on our phones are at a smaller scale, the amount of memory that we actually need to get all the pixels onto the screen on that smaller screen is less, and so that's okay that it has those things. But we're seeing that evolution of this mobile processor go from a single core with very little graphics. Let's bounce back to that real quick. Okay, so single core CPU with very little graphics. Graphics is just this dude, whatever this specific chip is. It's a single core again, and whatever its minimum capabilities are. We see the RAM as a whole lot less, and that's maybe less meaningful, but it's a lot less on this. So if the entry level, I think we saw on the other one, was 4 gigabytes, and the entry level here is 256 megabytes. That means the new one has 16 times the amount of memory at the minimum. We probably would also see a different clock rate, the speed of the processors. We did mention last time the use of the word nanometer. So in this original thing, I don't think it showed it in the other one, but we'll go check. This processor has 149 million transistors on it. And that has to do with that 3D printed circuit boards, where the smaller that nanometer measurement of the technology we're using to make the processors, the more transistors we can fit in the same space. So presumably, as we go through the history of these processors, we should see the number of transistors go up. But we shouldn't necessarily have, we don't actually have bigger processors. Okay, oh, and notice here it says this is a 45 nanometer process. All right, so this guy was 53 millimeters squared, is the actual processor. It holds 149 million transistors, 45 nanometers. Let's just jump to the very next guy in the evolution. Well, I guess I have to go to, let's go A5X. Okay, this is still based on the 45 nanometers, so we hadn't gotten better at doing that stuff yet. We see the GPU is a little bit more powerful. We see that we actually do have 2 cores now. So I guess let's just keep trucking. What I'll do is I'll just keep jumping by a couple. So that was the A5X. Let's do the A6X. Do we not get the specs on that guy? kind of has it over here. Let's get the one that has similar. Let's go to the A10. Give us similar specs. Okay, here we go. Okay, yeah. So here, I mean, this is several years removed, but you know, this is what 5, 6 years. I don't remember what the date was on the first one, but I think actually only 4 years from the second one we had brought up, which was still 42 nanometers. So this is 2016, you know, and this guy was using 16 nanometer technology. And now we have 3.28 billion transistors. And this guy doesn't give us the physical size of the processor, but I promise you it was not substantially different than the physical size of that older one. In fact, there's even a chance, stand up here, there's even a chance that it was a smaller processor. You know, but I think for our example here, we can operate off of, we can say they're roughly the same size physical processors, but we see that this guy had 3.28 billion transistors versus whatever the other one was, 160 million transistors. I mean, a substantial different amount of awesomeness was shoved onto this processor. And this was for a single core. And this guy had all these extra cores. So pretty impressive where we went. And this is just kind of, this is 2016. We jump even farther. Did the A15 give us, I don't remember if that guy gave us a the nanometer stuff. I think we're at like 4 nanometers. Why can't I click on some of these things? Like the page is unresponsive. Hey, this page is really, it just jumps all over the place. All right, A15, do we get nanometer? We don't. Go to A14, let's see if we get nanometer there. Well, we do get a number of transistors. So we have 11.8 billion transistors, and this is 4 years later from that other one, as opposed to whatever was the 3.6 billion. So this is going to use an even smaller nanometer thing. So, you know, we're kind of seeing this kind of this micro architecture where we're getting better and better and better at putting more stuff into the same amount of space, without going back here, introducing significantly more heat, well, using more power, giving off more heat, or using too many more resources. We did see that the amount of memory kept going up with those other processors and stuff. So they had 4 or 6 gigabytes as opposed to originally 256 megabytes. But if we think about our computers today, I mean, the computer I'm on right now, I think has 16 gigabytes of memory and an M1 processor. So we're going to be talking about these processors here soon. You know, but so this guy is, you know, something that I would view as sitting kind of between a smartphone and a full-fledged laptop. I use this guy often as a normal laptop. It can do everything a normal laptop does, but if you're going to start rendering video or something on it, something that's kind of heavy lifting, this guy is going to probably start having some performance issues pretty quickly. But in terms of normal everyday stuff, guy's going to work all day long. It's going to work pretty well. Okay. So, and that was from 2020, which is actually the same year we're looking at here. So this guy has 16 gigabytes of RAM in it. And in 2020 here, we were working with, did it show us our, oh, it doesn't show us our memory. I'm guessing it's probably six gigabytes of memory, something like that. But again, we're already dealing with these neural engines. So we're bringing that idea of that decision making to hardware, which allows us to have those things hopefully happen more quickly. You know, truth be told, we're not really using some of those neural things to their full capability yet, because as human beings, we've only started figuring out what things are neural networks good at and what things are they not good at. You know, I use the starting example today of my first experience with a neural network was to do multiplication. We don't need a neural network to do multiplication. Our computers can already do that with 100% accuracy super fast. It's interesting to say, oh, I can do it using a neural network, but we don't need it. So what are things that we can start using a neural network for? I use the example of like self-driving cars, where we have kind of this vague problem solving that human beings have, and we're trying to capture that without having the burden of trying to write a piece of software that takes into account every single little thing that ever happens when you're driving your car, and actually do that algorithmically. You know, if this is what I see, do this. If this is what I see, do this. Literally taking it all into consideration, as opposed to, as a human being, we react to new situations all the time, and that's what these neural engines are kind of meant to do. Okay. Why do I have 4 zillion people that are just randomly joining the class now? Okay. All right, so as we saw in some of those processors, the more modern chips, yes, they have more than one CPU core, but they are trying to create not all cores being equal. So we have some lower power cores and we have some higher power cores. Ultimately, all these things are paying attention to that concept of, oh, we need to preserve battery life. We need to, be good stewards of the resources we have available to us, and the more mobile the device is. We can't just do what we do on desktop and say, hey, here is, we're going to have AMD makes a 48 core server processor, which actually has 96 logical cores, and they actually make a dual processor version of motherboards for that. So you have 192 core processors. That's only going to be very beneficial for like a multi-user operating system, like a Unix-based operating system, where a whole bunch of different users are remoted into it at the same time, because otherwise you're not going to have that many simultaneous applications running at once that can actually take advantage of that many cores as an individual user. But like we saw a few minutes ago, we saw this giant heat sink for cooling. With that level of power is going to come a whole lot of heat, and we just can't have that in a smartphone. So we already have a ceiling on us for what kind of power we can put into a smartphone, even if we have the technological capabilities of making more powerful chips that are similar size. We have to play that game against heat. Actually going to go ahead and just jump down to, I'm going to skip this M1, the original M1 processor. That's well, let me just open it real quick. This is what's on the computer I'm on right now. And this is the cool picture they always show of this thing. And they call this guy something called a system on a chip. And that's actually something that's kind of impressive. If we start bridging away from smartphones a little bit, even though they've had systems on a chip for a while, but what we think of as a smartphone system is different than a laptop system, but we're still talking about the mobile world. If you were to open up a MacBook
Air from 19 or not 19 from like 2018 or something like that, before the M1 processor. What you would have found is here, let's actually go and look at this. Let's see, MacBook Air 2018 internals. Yeah, that's the whole computer. What I have hovered over right there. Okay, so on that little board, you have all your memory, you have your processor, you have your hard drive. Is a solid state drive, which you've looked at flash memory in one of your papers. You have all that stuff shoved onto that one little board, all soldered in there. You don't have components that are separately, replaceable. So one of the downsides to Apple that people maybe complain about is that you can't really replace stuff. If you have something that goes wrong on your MacBook Pro and you take it in, well, they'll charge you some money to do it, but they're going to replace the entire logic board. So you're going to get a brand new processor, brand new RAM, brand new everything for that, because everything is on this one little plate. Okay. Now, this is not a system on a chip. This is a motherboard with everything soldered on it. So now, why do you think that Apple moved towards having their stuff looking like this rather than let's just do a HP laptop 2018. Well, this gets us a good enough example. Actually, yeah, this is going to show what I'm looking for. So this is the inside of a gaming laptop from HP. So first of all, notice there's a whole lot more stuff going on in here. This is the hard drive down here. This guy's replaceable. I can open, if I were able to open up the laptop, I could yank this guy out. This is a 2.5-inch hard drive. I can go and buy off Amazon. I can buy any other 2.5-inch hard drive and I can plop it in here. It'll plug right in. This is serial ATA that is plugged in with. This is the memory. It's a replaceable memory. You see that it's in a little kind of a slot thing here. So you're going to have these two little metal bars over here. You just push them out. This guy will pop up at an angle. You just pull it out, go on to Amazon. You buy the right type of memory and a bigger capacity. You can pop that in and that'll work. So you have all sorts of up here is going to be your graphics cards. That's what's taking up a lot of space up in this area, because they're calling this a gaming PC. So this is going to have a mobile version of not a 3090 like we looked at, but a good graphics card for gaming that does give off more heat. That's why we have the two big fans up here and all that stuff. But the core question here is why did Apple do their entire system on that one little chip that you can't upgrade, you can't make any changes, as opposed to doing it something like this, where you can swap out the hard drive, you can add more memory, things like that? What do you think went into that decision making? And the answer is not just they like being jerks and they're proprietary. There might be truth to that, but that's not the real reason in this case. Anybody have a speculation as to why Apple put their entire computer basically on a single small circuit board, but everything was permanently mounted on that circuit board? It wasn't a plug and chug type thing where you can replace just the hard drive or just the memory.
Maybe to improve the optimization and performance.
Okay, tell me more about that. Well, why do you think that would improve optimization and performance?
So because the parts are in a more smaller form factor, Apple would be able to kind of make sure the parts can connect and communicate better, which would better optimize the power efficiency as well as um, performance across communicating with each other.
Okay, so if we look at just like this hard drive right here over in this HP, up here is where I said we have our serial ATA interface. So this bluish stuff behind the scenes here, that's the motherboard. This black thing here, that's the hard drive. So this motherboard has an exposed serial ATA interface that this hard drive will plug into. So whenever we say interface, we're kind of thinking about a middleman. This is something that lives between the two pieces of hardware that allows for communication between those two things. Now, whether or not there's drastic slowdown or not, the idea here, to your point, is maybe there is some speed loss because something had to travel through some sort of intermediary rather than being directly connected. That's probably a fair assessment. At least it's some maybe barely measurable level, but definitely there. I mentioned earlier, and especially, I mean, I see this in my, we're not seeing a example of this HP, but you can see this pretty easily if you go into like a Best Buy. You know, you look at non-Apple laptops, most of them are significantly thicker machines than Apple's laptops are. You know, especially Apple's MacBook Airs, look, I'm on right now, you know, their claim to fame is, you know, how impossibly thin they are, and you can chop vegetables with this thing. In order to accomplish that, you need to miniaturize as much stuff as you can on the inside of that device in order to squeeze the device being smaller and smaller and smaller while still giving enough physical space and what's left over to fit a battery. You know, and a battery can be in all sorts of different form factors, but you still need to get that battery into all the little nooks and crannies and, you know, any sort of open space that you have in there. If you can get battery capacity into that space, you're going to extend your battery life. So Apple's move would be, let's get everything onto this small little chip or the small little board initially, something like this, so that the entire rest of the internals there can be battery. So if we're looking at this here, we have battery, battery, battery. This is the controller for the keyboard. And then the computer's up here with one fan. So they're looking at putting batteries all over the place instead of having the motherboard all over the place. Now, when we jump back to what I had on this guy, we see the next step of this is called a system on a chip. So now instead of I gotta get a good this maybe let's just say this is good enough for our example here. So now this is your processor. And what you actually have is all your stuff is on just the processor. So the processor is there, the graphics card is there, your main memory is there. You know, these guys are using a unified memory architecture. So actually your hard drive storage can be on here as well. Your neural engine's on here. You also have cache. We'll be talking about that when we get into the ARM assembly dealing with system or the registers that are on the CPUs relative to, as you get farther away, you start using cache. But effectively, your entire computer is on this single chip. which allows you, or a high percentage of your computer is on this single chip, allowing you to either have smaller devices powered by this chip, or have more other capacities, other resources, room for those other resources while still having slim devices. Now, keep in mind, though, that shoving everything onto the chip like this doesn't necessarily solve all the world's problems, because this, you might imagine, this is probably going to be generating more heat than we were dealing with before. Let's see if we get any information on that in here. So just a couple of the things. So we have 4 high performance cores, 4 high efficiency cores. We have 8 GPU cores, 16 neural engine cores. We have several different other controllers that are on there, things that we didn't really think about for smartphones, but being able to plug USB devices in, stuff like that. You need to have some kind of controller for managing those kind of devices. We have an amount of RAM that starts eking up into, oh, this is actual computer memory, 8 or 16 gigabytes of memory. Clock rates here, we've got 16 billion transistors. We see that the dimensions of the processor are a little bit bigger than what we saw before, but we have so much stuff squeezed onto this still very small piece of real estate. So it becomes a pretty interesting architectural design. But we still have to then deal with heat with those guys. Now, as you move up through their latest processors, and you get to like their M1 Pro or M1 Max or M1 Ultra. M1 Ultra was just announced actually this month. See if they give us a picture of this guy, because what it does is it puts like 2 M1 Maxes next to each other. Yeah, so they actually just took the M1 Max and an M1 Max processor and linked them together, and now you have an M1 Ultra. So what does an M1 Ultra give us? Well, it gives us 16 high performance cores, 4 high efficiencies. We have 48 or 64 core GPU, 32 neural network engines. Then you have all your controllers for your external things. You can have up to 128 gigabytes of RAM, whereas the M1 Max only supported 64. So that's why it's one or the other. You can use the memory from just one of them. 114 billion transistors. And yes, it's bigger because now you have 2 larger chips, but now it's not just a chip, it's the entire computer. This is the size of the entire computer that's on there. And that chip right now is only available inside of the Apple, the Mac Studio, which looks like a tall Mac Mini. Yeah, so this is the Mac Studio. Just need to have it sit next to something so you can actually see its physical. Yeah, it's kind of like the size of a small toaster. Kind of the physical size of this thing. So pretty impressive stuff. All right, so let me stop that for a second. Then I want to go and look at next assignment. Make that available. do next Tuesday? Okay, so next homework is up on Blackboard. So it's to write a short paper discussing the high-level architecture of ARM-based processors. So I mentioned ARM today as opposed to Intel-based architecture. Specifically, what registers are available and how large they are. So maybe pick a recent ARM processor from Apple or Snapdragon. So I mean, what would be cool, you know, you don't have to do this, but what would be cool is for somebody to maybe look into something from an M1 processor or newer, which are still ARM based. But it would be interesting to see some of the number differences for the internals of an M1 compared to like one of the you know AX chips from Apple. But they're all going to be very similar things. So effectively, what you're going to be describing is what do the internals of that processor actually look like? How many hardware registers? How big are the hardware registers? That type of thing, because we're starting to trend towards, we're going to look at assembly language using ARM processors, and this is going to give us the resources that we have available for us. Okay, that makes some sense. And actually, if you wanted to get ahead, I'm going to actually go ahead and open up the next one, because we really already talked about this stuff. Comparing iOS versus Android over the years. This will help you fill in some of the gaps of the things we talked about. So I'll actually make that one just do next Thursday. But you've already gotten a lot of the information here in class that we been talking about. This just as you look into filling in the gaps between iOS and Android. Okay, so both of those should be open on Blackboard. Questions, comments, concerns, bribes?
What was the most recent ARM product you were talking about that you wanted compared to? You said it was
I mean, if any of the M1 chips, so you have the M1, the M1 Pro, the M1 Max, or the M1 Ultra.
Okay.
Yeah, and the M1 Ultra is literally two M1 Maxes put together.
But yeah, that's why I was saying. Yeah, that's why I was saying the most the greatest creativity is literally taking two devices and saying, "What if we put them together?"
Yeah, but I mean, it's even more embarrassing than that. They literally put two M1 Max chips next to each other and just link them. It's not even, they didn't even do it at the architectural level. They just said, we're gonna slap these two guys in here. We're just gonna wire them up. Now you got both. Go.
Yeah, take back my previous comment. I thought it was a little.
The
I thought they at
M1
least
Max,
put wire.
the M1 Max and the M1 Pro are separate processors. They're very similar architectures, but they are not built in terms of each other. The Ultra is built in terms of the Max. Okay, so I will see everybody on Tuesday.
Take care.
Yep, have a good one.
Thank you.